Hi there, welcome back to my channel, and in this video I'm going to take you through directional derivatives. In our previous lessons we've dealt with the partial derivatives, chain rule of different forms, so we continue with the directional derivatives in our calculus with several variables course. Please, if this is the first time being on this channel, kindly subscribe to support and please watch this video to the end. So when you say directional derivatives, what do we mean by directional derivatives? Okay, so it says is the rate of change of a function f of x, y, or it can be in any function. I just use this to represent a function. Okay, so it's the rate of change of function f of x, y in the direction of the unit vector w, which is equal to angle brackets a and b, right? So the rate of change of a particular function in the direction of the unit vector of a given vector. Okay, so it's generally represented as this. Whenever you see d and u with any function f of x or f of anything, this is asking you to find the directional derivatives. I have some problems here for us to solve, so let's quickly go through the problem so you understand this concept better. So I have, it said find each of the directional derivatives. So the A is saying that we should find the directional derivatives of a function at point 20. Take note of this, at point 20, where the function f of xy is equal to x multiplying e to the power xy plus y, and the vector is the unit vector in the direction of angle theta is given as 2 pi on 3. So here you have been given an angle to show the direction. Okay, you've been given an angle to show the direction. Then we have this second. So let's quickly solve the first problem. But before then, let's get back to the definition once again. So it said the rate of change of a function, right, in the direction of the unit vector. Take note. So a unit vector should have a magnitude of 1, right? Yeah, so for the start, what do I need? I need my vector. Then I will convert it to a unit vector. Then the next thing I need also is my derivatives. Then after I multiply, okay? After I multiply. So let's see how we can solve this problem well. Now, what is the vector given? We aren't given any vector, right? But we're given a unit vector in a direction of this. So, you know, once we're given a theta, so if you are on the Cartesian plane, okay, this is x and y, so this is 2D plane, okay? So we have our y, we have what, our x here. And I give you any function, and I give you the theta, right? I can find the x and y components as simply the horizontal and what vertical components of my theta, okay? But this is a unit vector, so meaning that from here to here is what, 1, right? So y is equal to sine theta, x is equal to cos what, theta. That is all. So since it's a unit vector, we can decompose our direction as what, y equals sine theta, and x is equal to sine and cos theta. So now let's see. Now our unit vector is simply equal to angle brackets cos 2 pi on 3, comma sine 2 pi on 3. So what am I getting for this? What is cos 2 pi on 3? So cos 2 pi on 3 is giving us, so 2 pi on 3 is actually what? 1. So pi on 3 is 60, right? So cos 120, right? So let's say cos 120 degrees, comma sine 120 degrees. Is that not it? Yeah. So let's see. So my unit vector then becomes negative half, comma square root of 3 on 2, right? Once I have my unit vector, the next thing to find is the partial derivatives, or you say derivatives, okay? Derivatives. So to find the partial derivatives, the function was given as this. So we need to find the x and y components of this function. So let me write the function from my side. So the function is given as f of xy is equal to x e to the power xy plus y. Okay. So if I want to find the derivatives of this function, I need fx and what? Fy. So what is fx? Differentiating this function with respect to x, every y becomes a constant. Okay. So I'll have this being a constant, but still this becomes by parts, differentiation by parts. Okay. Sorry. This becomes product rule. I was using integration here, so sorry. So it becomes product rule. Okay. So for product rule, I'll differentiate x, I'll get 1, maintaining e to the power xy, plus I'll maintain x and differentiate my e to the power xy. Differentiating e to the power xy, I'll differentiate the power here with respect to x and I'll get y, e to the power xy. Okay. Then here becomes 0. So obviously fx is equal to e to the power xy plus xy e to the power xy. Okay. So once you get this, then we can find the fy. So fy is also giving us differentiating this with respect to y. My x becomes a constant, right? So I only have exponential function carrying the y. I'll simply differentiate the power here, right? When I differentiate the power, I'll get what? X. Is that not it? So I'll have x, this x, multiplying the whole expression, x e to the power xy. Then this is y, so plus 1. This will give me s squared e to the power xy plus 1. Then you write your derivatives as a vector. That is, your derivative as a vector. Let me write this well. So we have fx comma fy giving us angle bracket e to the power xy plus xy e to the power xy, right? Comma, then fy comes, which is what? S squared e to the power xy plus 1, angle bracket. As simple as that. Okay. So with this one, when we say directional derivatives, we are simply going to multiply our derivatives dot our unit vector. So it's a scalar dot product of our derivative and each unit vector. So I simply have my negative half being the unit vector, comma square root of 3 on 2 dot e to the power xy plus xy e to the power xy, comma s squared e to the power xy plus 1. So at this point, I will simply do this multiplication. This multiplies this plus this multiplies this. That's simple, the dot products. Okay. So with here, I'll have negative half multiplying e to the power xy plus xy e to the power xy plus square root of 3 on 2 s squared e to the power xy plus 1. But we were given the directional derivative at a particular point 20. Okay. So wherever I see x, I'll put what? 2. Wherever I see y, I'll put 0 there. So negative half. You know that 20, everything will be 1, right? So I'll have 1 plus here to 20. So here will be 1, but here will be 0. So to take it away, so 0 plus root 3 on 2, right? Yep. So when I come here, 20, so the point is 20.20. So x should be 4, right? Then here will be what? Obviously 0, so 1. So 2 squared. So let me write 2 squared plus 1. Okay. So with this, I simply get negative half times 1. So negative half. And this is what? 4 plus 1, 5. Plus 5 root 3 over 2. Okay. 5 root 3 over 2. And this gives us our directional derivative. So take note on how to solve for directional derivatives. And in this problem, they were given an angle, not a vector. So let's see the second problem. So problem B, we were given this function here. We're given the function f of x, y, z to be this, and the direction of, so here we're given a direction vector. So let's see how we solve this one. So that one, let me write a function for my side, and I'll have f of x, y, z is equal to s squared z plus y cubed z squared, right, minus x, y, z. And the vector was given as angle -103. Okay, so at this point, what do we do? I said we need a unit vector, a unit vector. Find the unit vector. What's the unit vector? I need to take the length of this, or the magnitude. So I have -1 squared plus 0 squared plus 3 squared. So this is how we find the length. So this is 1 plus 9. So square root of 10, right? So the unit vector is simply equal to 1 over square root of 10 multiplying my vector -1, 0, 3. This is giving me -1 over root 10, 0, then 3 over root 10. Now I have my unit vector. The next thing to do is to find my partial derivatives, right? So my fx, when you have this function here, I want to differentiate with respect to x. Whatever unknown here becomes what? A constant, right? So x here, I'll get 2xz, right? For this side, there is no x, it will be 0. For here, there is an x, and I'll get what? -yz. When I differentiate the x, I'll get 1. So this is fx. What is fy? Fy to whatever which is not y becomes a constant. So my x squared z will be 0. Then here, I'll get 3y squared z squared. Then minus, when I come here, when I differentiate this with respect to y, I'll get -xz. Okay. Then finally fz to, I'll have here becomes what? S squared, and here I'm going to get 2y cubed z, then xz minus xy. So I now have all my three partial derivatives. Okay, so the directional derivative in this manner, which is capital D u, so here it will be capital E, capital D, you can say V, right? Our vector is V, but this is just representation. Okay, so capital D U of our f, which is x, y, z, is simply equal to, so this one, we weren't giving the directional derivative at a particular point. We are just finding the general directional derivative. Okay, so the general directional derivative is simply giving us, as I said, you multiply your partial derivatives by each of what? The directional numbers. Okay, we call these directional numbers. Okay, directional numbers. So you simply have -1 over root 10 multiplying your what? Fx, which is 2xz minus yz. Okay, plus 0 multiplying your fy. Okay, that is 3y squared z squared minus xz. Finally, plus 3 on square root of 10 multiplying x squared plus 2y cubed z minus xy. This 0 is so to go away. So our directional derivatives will simply be what? -1 on 10 multiplying on square root of 10 2xz minus yz plus 3 out of root 10 multiplying x squared plus 2y cubed z minus xy. And this brings us to the end of this lecture. Please don't forget to subscribe, like, and share.